Today, I will provide an overview of Laccase, an enzyme formerly known as benzene-diol dioxygen oxidoreductase. It is also referred to as urushiol oxidase. As a member of the multi-copper blue oxidase family, Laccase is highly valued for its exceptional catalytic versatility and broad substrate specificity. These three-domain glycoproteins are effective biocatalysts due to their unique capacity to function without the aid of external cofactor. Laccase are ubiquitous in nature, found across fungi, bacteria, animals, and plants. However, their biochemical properties vary significantly depending on their source. For instance, while fungal laccases typically exhibit high redox potential, up to 800 millivolts, and thrive in acidic environments, bacterial laccases are noted for their high thermostability and activity at higher pH levels ranging from 7 to 9.4. This diversity allows us to select specific laccases for various industrial applications, whether in free, immobilized, or recombinant forms. The molecular engine of this enzyme is its active copper center, which contains 4 ions, a mononuclear type 1 copper, and a trinuclear cluster consisting of 1 type 2 and 2 type 3 copper ions. The catalytic cycle proceeds in 3 distinct steps. First, substrate oxidation occurs at the type 1 copper site, which extracts electrons from phenolic compound or aromatic amines. Second, these electrons undergo internal transfer to the buried trinuclear cluster. Finally, the cluster facilitates a 4-electron reduction, converting molecular oxygen into water, which is the only byproduct of this reaction. In summary, the high oxidation ability and environmental friendliness of Laccase releasing only water make them indispensable in modern bioprocessing. Through protein engineering and directed evolution, we continue to adapt these enzymes for increasingly specific industrial function. That's all from me. Thank you.
Laccases are enzymes with high potential in food and beverage processing. They are mainly used in wine and beer stabilization because they can oxidize polyphenolic compounds. These polyphenols are responsible for haze, browning, and color changes in beverages. When lactase activity is well controlled, it reduces phenolic reactivity without affecting the taste or aroma. Laccase is also used to treat cork stoppers, where it oxidizes phenolic precursors that cause cork taint, helping to maintain wine aroma and quality. In beverage processing, laccases catalyzes the oxidation of phenolic compounds in wine, beer, and fruit juices. The enzyme uses oxygen and produces water as the only byproduct. This reaction converts reactive polyphenols into less soluble or polymerized forms. These compounds can then be removed during clarification or remain inactive, which helps to reduce heads, browning, and off flavors. Laccases work best under mild conditions. Its optimal pH is acidic to neutral, usually between pH 3 and 6. The ideal temperature is around 40 to 50 degrees Celsius, although some laccases are active at low temperature. Oxygen is required for the reaction, and the treatment time must be short to avoid over-oxidation. The main benefit of Laccase is to improve beverage clarity and color stability. It reduces haze in beer and turbidity in wine and juices. Laccase also supports sustainable and clean label processing because it uses oxygen instead of chemical additive. However, Laccase has some limitations. If not properly controlled, it can cause over-oxidation. This leads to unwanted browning and off flavors. Laccase activity also depends strongly on pH and temperatures, so unsuitable conditions can reduce its effectiveness.
In textile industry, the case is widely used for denim bleaching and wastewater treatment. It selectively oxidizes indigo dyes to produce a faded or worn appearance without damaging cotton fibers. Unlike harsh chemicals, the case operates under eco-friendly conditions and avoids the formation of toxic chlorinated byproducts. It is also applied after processing to detoxify and decolorize dye containing wastewater before discharge. In denim processing, lacase is applied in a single bath process, replacing pumic stone and hypochlorite. Mechanistically, lacase acts on insoluble indigo dye on the fabric surface. A redox mediator, such as NBTS, transfers electrons from indigo to the enzyme, enabling effective oxidation and color fading. The process operates under mild conditions, typically at acidic to neutral pH and moderate temperatures of 50 to 65 degrees Celsius. Residual dyes in the post-processing effluent are further treated with lacase into less toxic byproducts. The main benefits include improved fabric quality as Laccase does not attack cellulose backbone, preserving tensile and tear strength. Laccase produces distinctive gray cast and antique finishes that are difficult to achieve chemically. It also reduces water usage, energy demand, and washing steps while lowering chemical oxygen demand in wastewater, which reduces environmental pollution. However, there are limitations. Laccase enzymes and mediators are more expensive than conventional bleaching chemicals. Enzyme activity can decrease under extreme pH or temperature conditions and may be inhibited by ionic surfactants or heavy metals found in processing water. Additionally, Laccase is specific to indigo dye and ineffective for bleaching sulfur-dyed black fabrics.
The application of Laccase in bioremediation has gained increasing attention due to its ability to break down a wide range of complex pollutants. Researchers have applied Laccase to address various environmental contamination issues, including dye decolorization, soil remediation, and biobleaching in the paper industry. Among these applications, dye decolorization is one of the most widely studied, as Laccase offers an eco-friendly alternative for treating industrial dye that are often resistant to natural degradation. One well-known example is Ramazzo's Brilliant Blue R dye, which is an anthraquinone-based dye composed of 3 aromatic rings. During the decolorization process, Laccase oxidizes the anthraquinone ring system of the dye, generating unstable free radical. This radical leads to the breakdown of aromatic structure, disrupting the chromophore responsible for the blue color. As a result, the dye loses color. In this application, Laccase typically works optimally at a pH range of 3 to 5 and at a temperature between 30 and 50 Celsius. The use of Laccase in dye decolorization provides several environmental benefits. Laccase uses molecular oxygen as the electron acceptor and produces water as the only byproduct, making it a green and sustainable catalyst. In addition, Laccase can achieve decolorization efficiency of over 90%. The breakdown of dichromophore may also result in a less toxic byproduct, allowing the treated wastewater to be safely reused or discharged. However, there are also limitations to Laccase-based dye decolorization. The relatively low redox potential of Laccase limits its ability to directly oxidize many non-phenolic or high redox potential substrates without the use of mediator. Furthermore, small changes in pH or exposure to high temperature can also reduce the Laccase activity. Finally, the high cost of enzyme production and redox mediator can restrict large-scale industrial application of Laccase in bioremediation.
Laccase is the powerhouse for SDG 12, responsible consumption and production. It achieves sustainable chemistry use by replacing harsh chlorine with oxygen in textile industry. It reduces solid waste and oxidative browning to extend products' shelf life in food industry. Moreover, it detoxifies wastewater and mitigates pollution in bioremediation industry. To be critical, Laccase application requires safety awareness in workers and consumers. Granulated formulation and PPE are used to control Laccase inhaling that can cause allergy and asthma. Ethical testing is also required to ensure no active residual in final products. Laccase has the advantage to be biodegradable when it comes to waste handling. Spent Laccase is discharged into biological treatment wastewater plants to be digested. According to the Department of Occupational Safety and Health Malaysia, local exhaust ventilation or LEV is needed when handling enzyme. Furthermore, SOPs are strictly followed when handling gas-producing microbes and enzyme. For example, inactivating waste with heat and sealing properly to avoid enzyme dust. Finally, application can be improved by culturing Laccase-producing microbes in agricultural waste like rice straw to reduce the high production cost. In addition, enzyme immobilization is proposed to prolong enzyme lifetime and sustain Laccase application.